Good evening. This is February the 5th. This is Math 2414. A couple of announcements here at the beginning. The exam one window is coming up really quickly now. The window is open from February the 8th through the 13th. I've had a lot of people ask me in all of my classes about various different questions. Remember, unless you've worked something out with me separately, then you can take the test at any Lone Star College testing center. I'll send it to all the testing centers. You just have to make sure that the testing center you're going to use is open during the times that you need, and that you should allow yourself about 3 hours. So make sure that you pay attention to the time that the testing center you're going to use is open, because there is a little bit of difference from college to college and testing center to testing center. Graphing calculators are allowed on the test, and most of the Lone Star testing centers have graphing calculators that they can lend you for the test. No notes are allowed on the test, no formula sheets, none of that. It is a paper and pencil exam. It is not a multiple choice test. It's a test where you work problems, show all your work, and I'm going to be grading your work. The online office hours this week are Tuesday, tomorrow from 11 to 12, and then 8:30 to 9:30 p.m. And Sunday from 8:30 to 9:30 p.m. Remember that you can also make an appointment to come by and see me. And when I say come by and see me, remember I'm talking about in my WebEx office, and so you can make an appointment, and we can set up some kind of a time for you to come by and see me before you go in and take the exam. On-campus hours are, I'm going to be on campus, remember, before every exam I give during the semester for a couple of days. So I'll be on campus this Wednesday from 4 to 6 p.m. and on Thursday from 9 to 11 a.m. My office is at the North Harris campus in Winship 115K. So do not hesitate to come by during those hours, and you don't need to make an appointment necessarily to do that. It's never a bad idea to email me to let me know you're going to be there. But you can come by during those hours if you want to talk to me face-to-face and get some questions answered. Tiffany, can you hear me? Tiffany, are you there? All right, I don't know if you can hear me, Tiffany, but I cannot. Okay, you can hear me. I got your chat message. I can definitely not hear you, so I don't know if you have a microphone issue with whatever device you're using. Some people call in with their phone, and you were given that option as you logged in. You can also just click on audio and audio setup, and it should give you the option to call in with your phone. So you can do that, or you can just sit and listen and chat. Send a chat message to me with questions if you've got them. So that's up to you what you want to do. I would rather that I could hear you, certainly, if it's possible, but that's certainly up to you. So send me a chat message if you've got a question, okay? All right, so today we are going to talk about two things. We're going to look at integration. In fact, today is really all about integration. What we've been doing are applications of integration. So we've been doing area between two curves, volumes, arc length, surface area, centers of mass. We've been doing all those different kinds of things. And so now what we're going to do is turn our attention away from applications like that and turn our attention back towards actual kind of hardcore integration of different kinds of functions and dealing with integration. So now some of what I'm about to cover is going to be a review. And so that's good, because going into the exam, there will be some integration questions at the beginning on exam one. So exam one, those of you who watch this video, those of you who are with me live today, and those of you who watch this recorded, this is going to be good information for you. And the people who don't watch either one of these things are going to regret not being here. But exam one is going to start and I'm going to be very upfront, it's going to start with 8 integration problems. Now, I am not saying that these are going to be all difficult problems. They're not. Some of them are going to be very straightforward, but it's going to start with 8 integration problems, and it's going to cover the things we've been talking about in class, and I've been slowly working on over the first few lectures during the semester to make sure that you're kind of up to speed with integration. So all the things we've been talking about with U substitutions and completing the square, long division, splitting integrals, all of those kinds of specialized algebraic techniques are all things that I want you to be working on, and you need to be good at those things, or you need to know how to use those tools as you go through the rest of the semester. So I think it's really important that you go back and kind of review that. Those are things that you should have talked about in Cal 1, but Cal 1 is kind of a really variable quantity throughout the country and even throughout the state of Texas, and so it depends on where you took Cal 1, how long ago you took it, all those different kinds of things. So I'm trying to get you back up to speed with integration, because it's gonna pay off for you as you go through the rest of the semester, and it's gonna work against you the rest of the semester if you struggle with a lot of the basic things with integration. So that's why I've been talking about it throughout the lectures here at the beginning of the semester, kind of at the beginning of some of the lectures during each day. And today the homework problems that I give you that are due this coming Sunday are all problems that would be good review problems for your first exam. So these are the kinds of things that I want you to be pretty good at during the semester. Now, don't forget, the basic integral forms, and I'm not going to write them all down, but the key ones that we're talking about for the semester, and for right now at least, are the power rule, obviously u to the n du, and then the kind of companion to the power rule, right, where that you've got du over u. Remember, the power rule does not apply when n is -1, when the power is -1. The log rule does apply when that power is -1, right? So that's n equals -1 right there, right? Because that's u to the -1 du. And then you've got e to the u du, right? You've got those three kind of very important forms, and then you've got the trig functions that you certainly need to know. And I'm not going to write all those down, but then also don't forget you've got the kind of specialized forms for the tangent. Remember, the tangent's negative natural log of the absolute value of the cosine of u, plus c. And you've also got the specialized form for secant, which is the natural log of the absolute value of secant x plus tangent x. So don't forget those kind of specialized forms, because those could come up on any exam during the semester, including exam 1. And then don't forget the inverse trig functions. So you've got the form for du over a squared plus u squared, which, remember, or we've talked about being 1 over a arctangent of u over a plus c. And then you have du over the square root of a squared minus u squared, which we know is arcsine of u over a. And then you even have the form for arcsecant, and I'll be honest with you, I'm not going to ask you arcsecant on this exam 1. So this form, arcsecant, you won't see on exam 1, but it is something that's going to crop up somewhere during the semester, certainly. So I kind of wanted to write down some of the basic integral forms again, or at least the starts of the basic integral forms, and kind of remind you of some things, and to talk about the fact that this is going to be about a fourth of your exam grade. And remember, no notes, no formula sheets on the test. None of that is on the test, right? And so, I think I wrote that on the first page here, but remember, no notes are allowed, no cheat sheets of any type or formula sheets or anything like that. So you've got to know these kinds of things during the semester. There's no, you're gonna have a hard time if you don't know some of the basic integral forms during the semester. So now in the final exam, I will allow you to use something. We'll obviously talk about that way later in the semester. But in the final exam, you will have something to use then, but not on the regular exams during the semester. All right. Anybody have any questions about that? Those of you who are with me live today, anybody have any questions? Okay. Then today, what we want to do is that first of all, let's go back over integration. So what I'm going to do is look at some integral problems and kind of talk through how we approach integral problems again, and the forms that we're using, etc. And then we will look at some problems where nothing that we've covered so far this semester would apply. And so we need to start developing some other techniques for integration. And so that's what we'll finish the semester, finish the class meeting with. So, all right, so we start off with a bunch of examples here. So we start off with 2t plus 1 over t squared plus t minus 4 dt. So don't forget, one thing I've told you is if you have a fraction, like this one is, where especially if you have a rational expression where there's just a polynomial on the top and a polynomial on the bottom, like this one is. One of two things is going to happen. If the degree of the numerator and the denominator are the same, or the degree of the numerator is bigger, then try long division. But if it's like this one is, where the degree of the top is smaller than the degree of the bottom, then always check just to see if you have du over u, right? Which remember is the natural log of the absolute value of u plus c. So think about what if u is the denominator, how that would work in this problem. And look at this. If u is the denominator, then notice that du is just the derivative of that, which is 2t plus 1 dt, right? And that's just by definition there. And sure enough, what do you get? You get exactly du over u, right? If you tried to use the substitution here, right, when you substitute, you get du over u. Exactly in this problem. And so that would just be the natural log of the absolute value of u, or the natural log of the absolute value of t squared plus t minus 4. If you did not think of du over u at the beginning of this problem, then you were really going to have trouble with this. This was actually a very easy problem because it's in the form du over u just like it is. But I see all sorts of issues with a problem like this when a student just kind of overlooks checking for du over u to see if it fits that form. So that's one thing that's a big deal as we go through Cal 2 is don't forget to check that form. All right, next example. So, and please shout out for those of you who are with me live today if you have a question about something, because we're going to be moving through several examples here. So next example, you have 2 over 2t minus 1 squared plus 4. So if you notice in the denominator, you've got u squared, you've got something squared plus 4. So this is a problem where you would check to see if you've got an arctangent form, right? Because that's what you're looking for, is it fit this form right here where you have du over a squared plus u squared like that. And remember the form there, if it does fit that form, it's 1 over a arctangent of u over a plus c. So what do you do here? You look at the expression that's squared in the denominator. So that would be our our u value. So u would be 2t minus 1. And notice that would give me a u squared in the denominator. and then du would be 2 dt. That's perfect for what I've got right there, because that would mean that the 2t minus 1 is u squared, and then I've got 2t dt in the numerator. And a, the constant a, would be 2, because a squared is how the formula is written, how the integral form is written. So a squared would be 4, right? A squared would be that constant right there. And so a would have to be 2. So this is exactly the arctangent form. And so it fits exactly. So we can write down the antiderivative right away. This would be 1 over 2 arctangent of u over a. So that'd be 2t minus 1 over 2, put parentheses around that probably, plus c. So both of those integrals fit a basic integral form really identically, just like they were written. And so as long as we know the form, then we can write out the antiderivative for the form. All right, next problem. And I don't see a question here at all. So the next problem. Let's say we have this integral, negative 2x over the square root of x squared minus 4 dx. Now, this particular integral, you've got the square root of that quadratic expression in there, and that maybe kind of vaguely reminds you of the arc sine form. But if you flip back, notice the arc sine form has got to have a squared minus u squared. The constant's got to be first, and then the variable is second in that arc sine form, which is right there, which is not the order that this one's written in. So this is probably not going to be an arc sine. Instead, you've got the square root of some algebraic expression. So think about whether this problem might just be a basic u substitution problem, right? So rewrite the square root of x squared minus 4 that's in the denominator as x squared minus 4 to the negative 1/2, and try a u substitution and see if that works in this problem. So let u, and remember, anytime you have a function raised to a power, you think about a u substitution as a possibility. All right, so u is x squared minus 4 in this problem. That's the function that's raised to a power, so I let u be that function. Then du would be 2x dx. And hey, I've almost got 2x dx. I've just got a negative 2x dx in my integral. So really, you just have a factor of negative 1 there. And so what you could do is just take out that negative 1 outside the integral. And then what you have left inside the integral is exactly what we need for this substitution. So I'm ready to substitute here, right? And when I do that, I get the negative of x squared minus 4 to the negative 1/2 is u to the negative 1/2. And then 2x dx is du. This is just a power rule problem, right? When you have a function raised to a power, think about whether a u substitution is going to help you in the problem. All right, so what do we do here? We just write the antiderivative. That's not bad. That's just u to the positive 1/2. You put the reciprocal in front, which is 2, and then you've got that negative sign just kind of trailing along there, and then plus c. And so this ends up being negative 2 times x squared minus 4 to the 1/2 plus c. And you've got it. That's the antiderivative, right? And there's nothing else left to do there. If you did not think about a u substitution in this problem, you might have trouble. Jaime, what's your question?
Yes, on the last part, the u is supposed to be raised to the negative power.
Are you talking about the problem I'm working right now?
Yes, the minus 2u raised to the 1/2 is supposed to be negative 1/2.
No, remember you're writing the antiderivative down. So if you're talking about here at the very end, let me erase that again and let's do it again. Right, you're talking about right there at the very end of the problem?
Yes.
Remember, you add 1 to the exponent. So when I add 1 to the exponent, I had negative 1/2 there. And so when I add 1 to the exponent, I get positive 1/2.
Okay.
Right? And then,
Yeah.
because that's just negative 1/2 plus 2, negative 1/2 plus 1, right? And then the negative sign trails along, and then I put the reciprocal in front, like that.
Okay.
Is that, did I address your question?
Yes.
Okay. All right. And let me write this all out. By the way, at the very end where I wrote x squared minus 4 to the 1/2 power, if you wrote it as a radical, that's fine. If you wrote it as a fractional exponent, also absolutely fine. It does not make any difference how you write that. All right, next problem I'm going to look at. Let's see. Let's say we have secant of 3x dx. So now on this problem, remember, and I wrote this down on the opening screen or the beginning of the lecture a minute ago, but remember that the antiderivative for secant u du is the natural log of secant u plus tangent u plus c, right? That's a basic integral form that you can just write down the antiderivative for the secant. Now we have secant of 3x in this problem. So don't forget that what that implies then is that if u is 3x, then du would be 3 dx. And so don't forget that what that tells you is that you would have to put a 3 in here to substitute. And that means a 1/3 on the outside. So all that really implies here when you've got the secant of 3x is that you're going to end up with the reciprocal of 3 out front. And then it's just the basic integral form is all it is. So this is going to be 1/3 natural log of the secant of 3x plus the tangent of 3x. And then plus the constant. That would be the antiderivative. So if you know the basic integral form, then this is not a problem. But if you don't know that basic integral form, that you know the antiderivative for secant, then you're going to have an issue in a problem like this. And this exact same thing works for something like this, the tangent of pi x dx. This is exactly the same problem, same kind of problem as the previous one. Remember that the antiderivative for tangent u du is negative natural log of the cosine, absolute value of the cosine of u plus c. So this is exactly like the problem I just did. So since it's a pi x in there, when you write out the antiderivative here, it is this basic integral form, but you'll just end up with a 1/pi on the outside. So you have the negative of 1/pi natural log of the cosine of pi x plus c, right? In this case, u is pi x and du is pi dx. So again, that would mean you'd have to put a pi on the inside of the integral and then a 1/pi on the outside. And that's where that 1/pi comes from. So, I wanted to work those problems to kind of remind you about those basic integral forms. All right, next problem. So I think this is the 6th one so far. We have 3x over x plus 4 dx. So since there's 2 terms in the denominator in this one, you ain't going to be able to just divide this out term by term. But notice that in this problem, the degree of the numerator is equal to the degree of the denominator. And so when that's true, when the degrees at the top and the bottom are the same, this is going to be a long division problem where you take 3x and just divide it by x plus 4. Remember, if the degree at the top is bigger or if they're the same, then long divide it, and you ought to be able to come up with something that you can integrate. All right, so in this case, x would go into 3x 3 times, so you have 3x plus 12. You subtract 3x minus 3x is 0, and then 0 minus 12, because technically there's a 0 here with the 3x. That would be negative 12. So our remainder is negative 12 in this problem. And so what that means is I can rewrite this integral as 3. That's my quotient, right, from the top of the long division problem. And then minus 12 over x plus 4 dx. Remember that last fraction is always the remainder over the divisor. So it's negative 12 over x plus 4. And then this ends up being an easy antiderivative to write down, because the antiderivative for 3 is just 3x. And then 12 over x plus 4, well, that's just dx over x plus 4. The 12 is just a constant that comes along for the ride. So that's just du over u, right? Because if u is x plus 4, then du would be dx. And so that's just a natural log. So it's a natural log of x plus 4 and then plus c. So notice if you know the forms, if you're pretty familiar with the forms and the techniques, integrals like this end up being pretty straightforward. And you ought to be able to get through the integral in just a couple of steps. Even if you have to formally write out the substitution, that's fine. Not a problem at all. It just adds a step or two, but it's not too big a deal. All right, this next problem you have 2 over 7 e to the x plus 4 dx. And if you try all the different things that we've done here, this problem's a little bit more challenging. It's definitely tricky. It is not in the form du over u. If you tried that, it's not du over u. It's not u to the n du. Right? It's not a power rule problem. You could take the 7 e to the x plus 4 and bring it to the numerator to the negative 1 power. But that doesn't do you any good, right? It's not, because you don't have anything outside the parentheses there. And so it's not that form either. So this is a kind of, to be honest with you, an algebraic trick on this problem, that if you see the algebraic trick, hopefully you kind of store this in the back of your mind here, and you kind of bring it out when you need it. So this algebraic trick goes like this. What you want to do sometimes is take an expression where you're having trouble integrating and change the way it looks by multiplying the top and the bottom by the same thing, but multiplying by something that's appropriate. So like in this case, if you multiply the top and the bottom by e to the negative x, now the reason why you'd think of e to the negative x is because you have an e to the x in the denominator. So sometimes multiplying by e to the negative x will allow you to get something that is actually going to make your problem easier. So let's see what we get when we multiply here. You have 2e to the negative x in the numerator, and in the denominator, this is the distributive property. So e to the negative x, you've got e to the negative x times 7e to the x, and you add the exponents on those e's, and you end up with 7e to the 0, and notice that's just 7. So that's just a 7 right there, and then you get plus 4e to the negative x, and then that's dx. So now the integral looks a lot different than the original problem. So now try du over u and see if maybe now it does work. So let's do that. Let's actually write out that substitution. Let's let u be the denominator. Then du, so let's see, the derivative of 7 is 0. And then the derivative, let's see, the 4 comes down for the ride. The derivative of e to the negative x is negative e to the negative x. So you have negative 4 e to the negative x dx. And sure enough, that's kind of sort of what I have. It's not exactly what I have, but it's kind of sort of what I have. So that's good news. I can just take the 2 that's in the integral and take it outside the integral. And then instead multiply, what do I need to get this to work? I need to multiply on the inside by -4. And so that means I multiply on the outside by -4 in the denominator. In other words, the reciprocal. So that would give you a -1/2 on the outside. And then on the inside, in the integral, the denominator would be u. And notice the numerator would just be du. And sure enough, it's exactly du over u when you make the substitution. So that antiderivative is the natural log of u plus c. And so that would give you the natural log of, what's u? 7 plus 4e to the -x. Like that, plus c. And that's certainly a kind of a tricky problem. There's no question about that. And you've got this kind of algebraic trick of multiplying top and bottom by e to the -x, like that. What I want you to get from this problem is that sometimes multiplying the top and the bottom by an expression, sometimes it's like the conjugate of the expression, be creative about it. But sometimes that will allow you to get through a problem, because it'll allow you to take an integral that does not match any forms and write it in a form that does. So in this case, we had an integral that did not match any forms. When we multiplied the top and the bottom by e to the -x, we ended up with du over u. So we were kind of fortunate in that respect. But what I'm trying to do is I go through a lot of problems with integration, and I've done this throughout these first 5 or 6 lectures here, is give you a lot of different things to try, and so then you've got this kind of tool chest of integration, and you're just digging through this tool chest to try to find the appropriate tool for the integral that you're working on. That's really actually a really good analogy as far as a tool chest goes. So that's what I'm trying to get you to build up this tool chest for integration. All right, I want to do one last problem, and then another problem after this one will lead us into the main topic for the day. So here we have sine squared t cosine t dt. Now, what sometimes I see students overlook is the fact that when I have sine squared t, remember that's kind of an abbreviation for sine of t squared. And it's easy to overlook that, but remember that's what that means. And because that's what that means, I think, writing it or thinking about it that way sometimes pays off for you. So if you think about it that way, notice you have a function to a power, right? You have a function raised to some power. And so that would indicate that maybe a u substitution might work here, right? If you let u be the function, then sometimes that will allow you to evaluate the integral. So that's what we do here. We let u be sine t. Then du is cosine t dt. And notice, sure enough, I have a cosine t dt in my integral. And so this, sure enough, is exactly the power rule. You have sine of t squared would just be u squared, and then cosine t dt would be du. Also, don't forget that when I have a definite integral like this, and I use a u substitution, I'm going to change my limits of integration so that they're u values. Remember that these current limits are x values, right? And I want to change them to u values down here, because now the integral is with respect to u. So I want the limits of integration to be u values. So don't forget how when we have done this in class already, right? You're taking your substitution, u equals sine t. Whoops, and one slight mistake I made here is I said x values, but I meant t values, right? These are t values because the original integral was with respect to t. Okay, so if u is sine t, then when t is 0, then u would be sine of 0, which is just 0. So the lower limit was 0, and it's still going to be 0. Upper limit is pi, right? T is pi. And then notice what happens here. So you get u equals sine of pi. And sine of pi is also 0. So notice you end up with the limits of integration to be from 0 to 0. That's okay. Don't panic on that. Don't forget that you've got a property of integrals that states that if you're integrating a definite integral from a to a, that is always equal to 0. And so boom, you can stop right there and just write 0. And you got it. You've got 0 as the answer. Now, if you didn't notice that, some of you might have done this. You're still going to get 0, but if you had noticed that this was the power rule, in this integral, then some of you might have gone right to 1/3 sine of t quantity cubed like that, just using the power rule and then going from 0 to pi. But notice you get the same thing because you get 1/3 sine of pi cubed minus 1/3 sine of 0 cubed. And both of those are 0. So you end up with 0 minus 0 or 0. So either way, you're going to get 0 as the answer. And I certainly would not care at all which way you approach that. All right. Now, so I guess no questions. So the next example seems like it is a relatively easy problem. X e to the x dx. You know that e to the u du is just e to the u plus c, right? That's if you have an integral in the form e to the u du, that its antiderivative is just e to the u. Unfortunately, this one's not just e to the u. It's because you've got that x as a factor in front. And this is a multiplication problem. This is not something that we can do at this point. We do not have, there is not, let's see, so there is not a product rule for antiderivatives. Not like there is for differentiation. And so I can't write an antiderivative directly on this form. And so what we want to do, this is a perfectly good example of a kind of problem where we can pull out a technique that is very useful in Cal 2 and Cal 3 that's called integration by parts. Now, integration by parts, this is the single, probably most fundamental non-standard technique for writing an antiderivative. It's called integration by parts. And it is sort of, kind of, so I'll say kind of, a product rule for antiderivatives. Not exactly, but it's kind of a product rule for antiderivatives. And if you have a multiplication problem that's your integral, that the function that you're integrating, sometimes integration by parts will work. All right, so what we're going to do is we're going to derive the form for integration by parts. So this is actually a derivation right here, and it's not a long derivation. So what we're going to do is we're going to start with a multiplication problem, f of x times g of x. And what we're going to do is we're going to take the derivative of that multiplication problem. So we're taking the derivative of a multiplication problem. Now that's not what we're trying to do in the integral at the top, but we're trying to find an antiderivative. Here I'm differentiating, but just be patient. This is going to work out. So we just use the product rule, right? That's the first function times the derivative of the second function plus the second function times the derivative of the first function, right? That's just a product rule problem. And now what we do is we integrate both sides of this equation. And you're integrating both sides of the equation with respect to x. So you're literally taking the integral, you're integrating on this side right, with respect to x, and you are integrating this other side with respect to x. But when you integrate the other side, since it's addition, let's just go ahead and integrate each term, integrate it term by term. So you have two integrals over here. We know we can integrate term by term, like that. All right, so now on the left side, what are you doing? You're integrating a derivative, and when you're talking about antiderivatives and antidifferentiation, what you're really saying there is, you've kind of got inverse processes there, and so you're left on this side with just f of x times g of x, right? Since you're integrating a derivative with respect to x, you're integrating with respect to x a derivative with respect to x, and so it's kind of like, right, that they're inverse processes that kind of sort of like cancel each other out, and you're just left with the original function, just f times g on that side. And on the other side, I'm just going to write this in a little bit more informally, just as f times g prime dx plus, and let's see, that last one, oh, and I think, yeah, I did miswrite this, and so I apologize for this. If you go back up to the original statement, this should have been, and I didn't write that. I said f times g prime, and then it should be plus g times f prime, and I didn't write it that way at all. And as I was looking back, all of a sudden I realized that there's something wrong with what I wrote. So this should be the integral of g of x times f prime of x dx. And so then this is just g times f prime dx. Okay, so I made that one little mistake there, so be careful to go back and fix that. So now what I'm going to do is I'm going to make a substitution. I'm going to let u be f of x, and I'm going to let v be g of x. Now, if u is f of x, then what that means is that du would just be f prime of x dx. And if v is g of x, then that would be dv is equal to g prime of x dx. And so now what we're going to do is we're going to substitute into that expression. So now substitute. When I say substitute, we're taking this form right here, and we're going to write it in terms of u and v. Excuse me. So f times g would just be u times v equals, and then you've got f times g prime of x dx. So f is u. If you look at this here, right, f would be u, and then you've got g prime of x right there. Right, and so notice that when we make these substitutions, you're kind of looking at that as pieces there, and so f would be u, and then g prime of x would be dv, and then plus the last one again. That's it, kind of in two pieces there, right? Let's see. So you've got g right there, and then you've got f prime of x dx to be a different quantity. So you're separating that one out into pieces. So the g is equal to v, and then f prime of x dx is du. So you've got the form, or you've got the expression written in kind of a nice form there at the end. And so what we do is just kind of move some terms around here, and we come up with this form right here. And that's that if we have u dv, then that would be equal to u times v minus the integral of v du. And that form right there is called that's the integration by parts form. Now the u dv are the parts right there. When you see the word parts, what you're doing is you're taking an integral and you are separating it into two pieces. These are the parts right here. One of the parts is u, and the other part is dv. Is dv. And so the idea is to separate the integral into two parts, two pieces, one of them being u and the other one being dv, and then literally calculating everything you need to write out the form to the right there, which is u times v minus the integral of v du. And so that's the process. And sometimes picking the parts is not an easy thing to do, but that's what we're going to look at here for a little while in class here. All right, so we're going to start off with the problem I have at the very top of the screen here, just x e to the x. So that's going to be our first example. We're going to look at this integral, x e to the x dx. And so that you've got, and actually let me move this down a little bit, and let me write the integration by parts form at the top of the page here, so that we have that written in front of us. So you've got the integral of v du is equal to u times v minus the integral of, I've written integration by parts down a million times, and I got that one backwards. So, so this is going to be u dv right here. So you have u dv is equal to u times v minus the integral of v du. So what we're going to do here is we're going to kind of make a little chart each time when we set this up. We're going to pick u, that's one of our parts, and then we're going to also pick dv, that's the other part. We're going to pick those two, and then once we've picked u, we will calculate du, because we need that. And once we pick dv, we will calculate v. And how are we going to do that? In each case, what are we going to do? We're going to differentiate here. So this is differentiate. And then on this side, with going from dv to v, what are we going to do? We're going to integrate or find an antiderivative. So notice when you set this up, and this can be confusing for students, is that you're doing both differentiation and anti-differentiation kind of in the same step right here. Also, this is critical. Integration is harder by a long shot than differentiation. So when you pick u and dv, dv in particular has to be something that you can actually integrate. When you put something over there, you better be able to integrate it, or you're not going to be able to get through the parts like you've got them. So that's critical to how you pick u and dv. All right, so in this problem, what I'm going to do is I'm going to pick u to be x and dv to be e to the x dx. Right? dv is just everything else in the integral. Once you've picked u, what do? You calculate du, and you just differentiate there, and you get du to be 1 dx, or just dx, right? Because the derivative of x is 1. And for dv equals e to the x dx, right, I integrate to find v, but the antiderivative for e to the x is just e to the x. All right, and then, okay, so I've got all the calculations done, so now I write down the integration by parts form. So that diagonal, notice that represents u times v, and then if you multiply straight across here, that's the integral v du right there. Right, so you do down the diagonal there to get u and v, u times v, and then multiply across the bottom row there and you get v du. All right, so let's write out the form. So this would be u times v. This would be x e to the x minus the integral of v du. V is e to the x, and then du would be equal to dx. And the question is, at this point, can you integrate what you've got? Have you made your life easier by going through this integration by parts? And the deal is you have, because the integral now is super easy. Just the antiderivative for e to the x is e to the x. And boom, all of a sudden you've got it. It just falls out right away. Right? And so this is, the key here is this an easier integral than the original? Is this an easier integral compared to the original? Right? That's what you're trying to do with integration by parts in most cases, is make that integral easier. Notice I said in most cases. There's going to be some exceptions to that. All right, so let's look at another problem. We're going to look at a bunch of problems here and a bunch of techniques. So again, shout out if you have a question about something, because we're going to just start going through and looking at different kinds of problems and how you separate them out. That's the key, is how do you pick u and dv at the beginning? And there's all sorts of different strategies for picking u and dv, but remember the key here is that whatever you pick dv to be, it has to be something you can actually integrate. If it's not, then you can't work the problem, right? So I pick u and dv in this case, and I'm separating this integral out into two pieces. Now notice that natural log that's there, don't put it over with dv, because that would be a problem, because I don't know what the antiderivative is for the natural log of x, right? So this is a problem right here, right? That's not going to work. So what do? You pick u and dv. Well, let's see, so I put the natural log of x over here with u then, and then everything else would go over here with dv, and so this would be 1 over x squared dx. And so then from u, I'm going to calculate du. Let me make that a little bit neater here. So du is going to be what? And then from dv, I find v. So, okay, this is not so bad. The derivative of natural log of x is just 1 over x dx. So du would be 1 over x dx. dv is 1 over x squared dx. And remember, that's just x to the negative 2 dx. So you can integrate that using the power rule, and that would just be negative x to the negative 1, or negative 1 over x. And now we write out the integration by parts form and see if we helped ourselves at all. Right? So you multiply down by down the diagonal there, and then you multiply across the bottom row to write out our integration by parts form. So uv would be negative 1 over x natural log x. That's my uv, u times v. And then minus the integral of v du, so that's negative 1 over x, that's v, and then du is 1 over x dx, like that. And notice this will work here, because you've made your life easier in this problem. First of all, this is going to be plus, and then this is just 1 over x squared when you multiply those together, which is just x to the negative 2. It's just a power rule. It's 1 over x squared. And so you end up with negative 1 over x, natural log x, and then the antiderivative for x to the negative 2 would be x to the negative 1, and then a minus in front, right? Because you're writing the reciprocal in front. And so it ends up being that it works out relatively straightforward at the end. You have negative 1 over x, natural log x, minus 1 over x plus c. All right, so hopefully we're okay, that there's no questions here. And I don't see any questions from anybody, so let's go on to another example. You know, right now, the best thing to do is, now there are some things that I'm going to need to show you on integration by parts here. Let's work another problem that's somewhat similar to the last one, but ends up being a problem in the middle there. So you have t natural log of t plus 1 dt. It's a multiplication problem, so that kind of sort of gives you a good indication that maybe parts is the way to do the problem. It's got a natural log in it. So when we pick u and dv, I don't want the natural log over there with the dv. So the natural log has got to go over here with the u. And then that would mean that dv is t dt, right? Everything else goes there with dv. All right, so if u is the natural log of t, then du is just the derivative of the natural log of t, is just 1 over t plus 1 dt. And then if dv is t dt, then the antiderivative there, that would be just a power rule. And that would be 1/2 t squared. And you don't write the plus constant there at the end when you're integrating right there, because you're going to take care of that arbitrary constant at the end of the problem when you finally evaluate the antiderivative. So you don't worry about a constant in that step right there. All right, so then we write out the integration by parts form. And remember, that's u times v minus the integral of v du. So you're multiplying down across the diagonal right here, and then multiplying across the bottom like that. So when you do that, u times v would be 1/2 t squared natural log of t plus 1. That's never the issue. The issue is always going to be this integral and whether you can actually do this integral. And so this is minus, and there's a 1/2 there that I can move outside the integral. And this is t squared over t plus 1 dt. Okay, so now the question is that integral easier? And I don't know if it's easier necessarily at all. It's not 100% straightforward, but at least there's something to do now on that t squared over t plus 1. I mean, because the degree of the numerator is bigger than the degree of the denominator, we talked about this before, this would be an example where long division actually comes into play. Yuck. And so we've got to take t squared and divide it by t plus 1. So, don't forget all those other things we've talked about during these first 5 or 6 lectures of the semester, and all these little algebraic tricks that you can use. So when we divide here, you multiply by t, and that would give you t squared plus t. Then don't forget you subtract, and so that gives me negative t. And then t goes into negative t minus 1 times, and you get negative t minus 1. Remember, you're multiplying there, so you're taking negative 1 times t plus 1, and that gives me negative t minus 1. Don't forget you're subtracting here. Lots of places to make a sign mistake here. So you have negative t minus negative t is 0, which is supposed to happen. And then you just end up with a positive 1 there as the remainder. So what you've done here, let's see, you've got 1/2 t squared times the natural log of t plus 1 minus 1/2 times, and now this integral, remember what we do after we long divide, we write down the quotient, which is t minus 1, and then we take the remainder and put it over the divisor. So this is 1 over t plus 1. And then that would be dt like that. And that, sure enough, is an integral that we can do. So you have 1/2 t squared natural log of t plus 1 minus 1/2 times, and I'm going to put this integral in brackets here, and then I'll multiply it by 1/2 at the end. you get 1/2 t squared minus t, and then the antiderivative for dt over 1 over t plus 1 is just the natural log of t plus 1. So this is the natural log of the absolute value of t plus 1. And then don't forget the constant at the end. You know, and to be honest with you, a lot of times in textbooks, you're going to see lots of different things happen here at the end as far as how to deal with this expression, whether you factor something out. I'm not going to make that big a deal about that at all. If you multiply through by negative 1/2, which is what I'm doing here, that would be okay. And there is a 1/2 that's common to all those terms, and so a lot of times in a textbook, you'll see that written out. To be honest with you, if you can get to that point of the problem, I am going to be absolutely thrilled, and I won't care about that little nitpicky stuff at the end at all. All right, so the next problem, and let's see, I'm kind of keeping an eye on the clock here. This next problem, I'm going to show you a shortcut that occurs sometimes for integration by parts problems. And I think that then there's some harder integration by parts problems that I think I'm going to save for the next class period. And I know I said harder integration by parts problems, and some of you might be saying at this point, gee, I thought these were hard enough as it was. And you're right, but there is something we need to talk about as far as integration by parts that is more involved than what we've done so far. But I do want to give you a little bit of a shortcut that will occur that applies in a problem where you have a power of x times an exponential function, and where you have a power of x times a trig function, like sine or cosine. When you have an integral that fits one of these kinds of forms, this shortcut's going to work relatively pretty well here. And so let me show you how this works. First of all, if you tried integration by parts here, it makes sense to let u be x cubed and dv to be sine x dx. You don't really want x cubed over there with the dv, because when you integrate it, it just makes it the power bigger, not smaller. So it makes sense to put the x cubed over there with the u. And then du would be 3x squared dx. And then v, the antiderivative for sine, remember that's negative cosine. That's the antiderivative for sine. So if we write the integration by parts form, u times v minus the integral of v du, you multiply down the diagonal like that, and then multiply across the bottom, and you end up with negative x cubed cosine x plus, because there's two negatives there, plus 3 times the integral of x squared cosine x dx. And so notice if you compare that integral to the original integral, it kind of looks a lot like the original integral. The only thing that's different is the power is smaller. So note integration by parts. Reduce the power by 1. When this happens, there is a shortcut. What that means is what we'd have to do is we'd have to go through integration by parts 2 more times to get to an integral finally that we can do. Means parts needs to be used two more times. To get rid of the x's. And what I would say at this point is yuck, right? I don't really want to have to do that and go through integration by parts a bunch more times if I can avoid it. And this shortcut works for these kinds of integrals at the top right here. And it's called the table form of integration by parts. Our textbook does not include the table form of integration by parts, but you'll see this in all sorts of other textbooks certainly. But in the OpenStax textbook, the authors did not cover that. But I think this is a good thing to know, definitely. What you do is you take your original integral and you make two columns, and you label one of them with a D and the other one with an I. The D just stands for derivative, and the I stands for integral. And you put one factor in one column and the other factor in the other column. And then the derivative, the x cubed, you just start differentiating x cubed over and over again. So you get 3x squared, 6x, 6, and 0. In fact, you integrate until you get to 0. I'm sorry, you differentiate until you get to 0. And then the I column, the sine x, you integrate the same number of times that until you get to that 0 there. So remember, you're integrating here. So this is negative cosine x, and then negative sine x, and then finally cosine x, and then sine x, like that. And then what you do here is you multiply down the diagonals. Multiply down the diagonals. And you alternate. You got to do two things here. You got to alternate between adding and subtracting. So this is, and I know that sounds kind of confusing here at first, but you'll understand this when I do this. Here's a diagonal right here, right? And what you do is you take that diagonal and you add it. You take that first one and it's always add. And then you take the next diagonal. You multiply there. The next diagonal is 3x squared and negative sine x. And what do you do with that diagonal? You subtract it. And then you just alternate between adding and subtracting here. Let's see, so here's another diagonal, 6x cosine x, like that. That one you're going to add. And then the last diagonal, 6 and sine x, like that, that one you are going to subtract. And if you just go down the diagonals like that, you actually you're writing down the antiderivative. And you are actually kind of going through the multiple levels of integration by parts very concisely. So you end up with negative x cubed cosine x minus, be careful of the SIGNs, minus 3x squared sine x plus 6x cosine x, and then minus 6 sine x, and then finally plus a constant of integration there at the end. Right? And you've got the antiderivative. And that's a heck of a lot more efficient to write it out that way than if you had to do integration by parts 3 separate times. All right, I want to do one more problem with the table form of integration by parts, and then that will be all we're going to do for the day. And then I'll see if there's any last questions here. So this problem is x to the 4th e to the 2x dx. Right, you've got that power of x times an exponential function. So this is a classic example where this integration by parts using the table form is more efficient. Because it's x to the 4th, you'd actually have to go through integration by parts 4 times to be able to deal with this integral. But instead, we're going to use the table format. So I put x to the 4th in the derivative column and e to the 2x in the integral column. And then you start differentiating x to the 4th. Remember, this is differentiating. So this is 4x cubed, 12x squared, 24x, 24, and then 0. Now remember, the second column is the integral column. So you're integrating, you're not differentiating, you're integrating e to the 2x. And so when you integrate, this is 1/2 e to the 2x. And what's going to happen? Every time you're going to get another 1/2 e to the 2x. So this next one will be 1/4 e to the 2x, and then 1/8 e to the 2x, and then 1/16 e to the 2x, and then 1/32 e to the 2x. And then don't forget that what you're doing next is you're looking at the diagonals. And you're going back through here, looking at the diagonals and multiplying these out like this. So you need to kind of keep things straight here. Some of you have trouble with neatness, and so that can be an issue. You have to watch for that. So those are the diagonals, and remember, you are adding the first diagonal, subtracting, adding, subtracting, adding, like that. That alternating the signs just comes from the fact that integration by parts is a subtraction problem. And so our antiderivative goes like this. You just start multiplying, and adding and subtracting is appropriate. So you have 1/2 x to the 4th e to the 2x. And then the next one is going to be a 4 and a 1/4, so those cancel, and so you just get x cubed e to the 2x. And then the next diagonal will be 12 times 8, which is 3/2, x squared e to the 2x. The next diagonal is going to be minus, and this is 24/16, which is also 3/2, and that would be e to the 2x. And then the last term would be just 24 times 1/3/2, so that would be 3/4 e to the 2x, and then plus a constant of integration at the end. And there's your antiderivative. It's really not a hard process to do. It can, in this case, it's a little bit lengthy, but a heck of a lot more efficient than having to use integration 4 times altogether there. All right, so I've got some more integration by parts problems to do. So what I'll say is integration by parts. So integration by parts, part 2, next week. Now don't forget that this week, no live lecture on Wednesday, and no live lecture next Monday. So no live lecture Wednesday or Monday, because that's going to be our testing window. And so the next live lecture won't be until February the 14th, Valentine's Day. So something to look forward to. So a great way to spend Valentine's Day is to have a calculus lecture. All right, so anybody have any, for Tiffany and Jaime, you guys are both listening to me today. Do either of you have any questions that you need to ask about? Jaime, do you have any questions?
No.
And I did get a comment, certainly that I totally understand this comment, by the way, that Tiffany kind of suggested that this was a lot of material and there's a lot of problems, and I kind of went through them kind of briskly. There's absolutely no question about that. I definitely agree with that. And so the idea here is to take it slowly as you start looking at homework problems and work your way slowly through these. And believe it or not, most people can work their way through this and start getting the hang of integration by parts. And so it can be intimidating at the beginning. I absolutely understand that. And I definitely get that reaction a lot when we deal with integration by parts. But it's not something that you can't get through. And I'm here to help you get through this. Remember that I have office hours, both face-to-face and online office hours, and I'll make an appointment to talk to you outside of those if I need to. But I am here to help you get through this. And then obviously just emailing me questions is always an okay thing to do. Now I'm going to finish this by pointing out that I'm going to assign 3 homework problems that are due on the 11th this week. These are 3 integrals, and this is all great practice for the exam. So the way I look at this is that these are practice problems for the exam, And let's just, so these are going to be on these notes, but these are the 3 problems that are going to be due. The first problem, I'm going to go ahead and tell you, is a long division problem, right? That's what you're going to try to do there. The second problem is completing the square in the denominator and the arctangent form. And the third problem is splitting the integral. We have done all of those examples in class before. In this case, splitting the integral into 2 separate integrals. We've done problems exactly like every one of those, in fact, in class and during lecture. So those 3 are due on February the 11th. And that's actually, you'll find that those are not going to be too bad of problems. So Tiffany and Jaime, both of you, if you have questions, you do not hesitate to come by.